Dear student, in the previous lecture, we have discussed about the working and designing of ideal differentiator circuit. In this lecture, we will discuss about the frequency response of ideal differentiator circuit and the limitation of ideal differentiator circuit, and then discussed about the practical differentiator circuit. The gain of operational amplifier differentiator is directly dependent on the frequency of input signal. Hence, for DC input where f is equal to 0, the output is also 0. As the frequency of input signal increases, the output also increases. The frequency response of an ideal differentiator is as shown in figure this. The frequency f1 the frequency f1 is the frequency for which the gain of a differentiator become unity or 0 dB. It can be seen from the figure that for frequency less than f1, the gain is less than unity. For f1, the gain becomes unity, that is 0 dB, and beyond f1, the gain increases at 20 dB per decade. And after f1, the gain increases with plus 20 dB per decade. For an ideal differentiator, the gain increases as frequency increases. Thus, at some higher frequency, the differentiator becomes unstable and cause oscillation, which results in noise. So, to avoid these two conditions, that is instability and noise, we have to shift from ideal differentiator to a practical differentiator circuit. The practical differentiator circuit can be designed if we place or use a resistor R1 in series with input capacitor and a capacitor CF in parallel with the feedback resistor RF as shown in figure. Here R1 is the input resistance used in series with C1, and here the CF capacitor is used in parallel with RF. The output voltage of a practical op-amp differentiating amplifier is given as V out is equal to minus RF C1 derivative of V in. The addition of resistor R1 and CF stabilize the circuit at higher frequency, and it also reduces the effect of noise on the circuit. We can say that the addition of R1 and the capacitor C1, it provides the stability at higher frequency as well as it reduces the impact or effect of noise on the circuit. The gain of a practical differentiator increases with increase in frequency, and at a particular frequency f1, the gain becomes unity 0. This is the f1 frequency where the gain is 0. The gain continues to increase at a rate of 20 dB per decade till input frequency reaches a frequency f2, which is shown in figure this. This is the frequency response of ideal differentiator, and this is the frequency response of a practical differentiator. Differentiating amplifiers are most commonly designed to operate on a triangular and a rectangular signals. They also find application as wave shaping circuits to detect high frequency component in the input signal. So, so far in this lecture, we have discussed differentiator amplifier is an inverting amplifier circuit configuration which uses reactive components such as capacitor, capacitor. Then we perform the mathematical differentiation operation on input signal with respect to time. They are commonly used on a triangular and rectangular signals, and thus they are used in wave shaping circuits. In the next lecture, we will discuss about the differential, sorry, we will discuss about the instrumentational amplifier. If you have any type of query, please write to me on my email address. Till then, bye bye. Thank you.